Hello grade 12s. I'll be making videos for each of the questions in the recent rates of reaction and equilibrium test. We'll start off with the multiple choice. Now immediately when I look at this question, I recognize that this is a Maxwell Boltzmann distribution curve. The area of both of these curves, TL and TM, represent the exact same amount of molecules. The only difference is we can see for TL, if we look where the majority of the molecules are, they're at a lower kinetic energy than TM. So that's telling us kinetic energy is directly related to temperature. And so it's telling us that TM is at a higher temperature than TL because the majority of the molecules have a higher kinetic energy. Just a reminder that the temperature change doesn't affect the activation energy. Only the catalyst affects the activation energy. So let's have a look. It says the graphs alongside give the distribution of molecular energies for a mixture of gases that react with each other. If TL and TM represent different temperatures at which the reactions take place, select the letter of the most correct statement below. So if they're comparing temperatures, remember what I said? TL will be lower than TM because the kinetic energy of most of the molecules of TL are lower than that of TM. So we're looking for TL at less of a temperature than TM. So that makes C and D incorrect. So let's see here for A. It says TL is less than TM. That is correct. At TM, the activation energy is lower. So remember what I just said. The activation energy is linked to a catalyst. If you include a catalyst, then we'll lower the activation energy. Otherwise, we don't change the activation energy. So let's look at B. TL is less than M. Yes. TM, more molecules will have kinetic energy higher than the activation energy. That is true. We haven't adjusted the kinetic energy. With the increase in temperature for TM, the molecules have more kinetic energy, which increases the possibility of the molecules colliding with successful collisions and with energies above that of the activation energy. So the answer is B. The graph below represents the changing concentration of reactant against time for a chemical reaction. Now, often we look at maybe the volume of a gas produced, and then it would start at zero because it's a product, and then the concentration of the gas would increase until we've used up our limiting reagent, and then the concentration would be constant, indicating that our reaction has reached completion. But here now we're looking at the reactant. So obviously the concentration of the reactants as they get used up to make products decreases. So that's a decrease, and that would indicate that the concentration is constant. It means then our limiting reagent has been used up. And so that would be some excess left over. So it says, in which of the following graphs does the dotted line show the effect of a catalyst? So all the catalyst is going to do, it's not going to influence the amount of product that we get or the amount of reactant that's used up. It just influences how quickly it gets done. So the line because this would be the concentration of a reactant that's left over. So it's not going to be the limiting reagent because the limiting reagent is always used up. So at this point, the limiting reagent would have been used up. So there's a concentration of the excess reagent that didn't get used. And that's showing us that it's reached completion over there. And so over here, the dotted line is indicating that the reaction is quicker. And that's what a catalyst does. So the answer is A. It can't be B because B, the reactant's getting used up slower. It can't be C because even though it's quicker, we're not going to influence the amount of the reactant that gets used. And again here, we're not influencing the amount of reactant that gets used. A catalyst only makes it quicker, but it doesn't change the amount of reactant getting used up or the amount of product being formed. So the answer is A. In a series of experiments, 0.05 gram samples of magnesium are added separately to 100 centimeter cube volume of hydrochloric acid. The table below summarizes the experimental conditions. I want to remind you, if you added more volume of the hydrochloric acid, but it was the same concentration, you would not influence the rate of the reaction. If you added more volume of a gas, then you have more particles per unit volume. Then it would influence the situation, because then you've changed the concentration of a gas. But if you have a solution and you just add more volume of a solution with the same concentration, it doesn't influence rate. Volume doesn't influence the rate of a reaction. It just influences it in terms of if it's a gas, because if you reduce the volume, then you're increasing the pressure. Or if you are adding more particles of a gas to a certain volume, then you've increased the particles per unit volume, which means you've increased the concentration. So let's have a look here. It's saying, in which of the experiments would the magnesium be expected to take the shortest time to react completely with the excess hydrochloric acid? So over here we can see that we've got powder and we've got an increased concentration of the sulfuric acid. And so definitely it's going to be number 4. Then if we have a look at number 3, it's also powder, which we've increased the surface area then of the magnesium. The concentration of the HCl is the same, but look at the temperature. The temperature has increased. And so number 3 and 4 would definitely use up the magnesium more quickly. The ones that are ribbon, even though we've increased the concentration of the HCl, that HCl can only react on the outside of the ribbon. And then once that layer has been reacted, the next layer. So because it's got such a low surface area, this won't have much of an influence. So number 3 and 4, because it's in powder form with the increased surface area. Here we have a high temperature, and here we've got an increased concentration. So that's definitely going to influence how the magnesium gets used up, and it will be used up the quickest in 3 and 4. Even though 5 is a powder, the temperature's decreased, so that will reduce the rate of the reaction. Then the last multiple choice, it says methanol can be produced by the following. So here we have the equation, and delta H less than 0 is telling us that the forward reaction is exothermic. Remember, if we cool the system, we will always favor the exothermic reaction. So if we cooled this system, we would favor the forward reaction, which produces heat. If we heated the system, it favors the endothermic reaction. So we would favor the reverse reaction. If we increase the heat of the system, we would favor the reverse endothermic reaction to cool the system. Then a reminder about pressure. Pressure only influences gases. We do have gases over here. And then it only influences if we have a different number of molecules as reactants and products. So here, from the balancing, that's 1 plus 2, so it's 3 over here, and it produces only 1 molecule. So if we increase the pressure of this system, it would favor the side with the least amount of molecules, because then you have less collisions and less successful collisions. If we reduce the pressure, it would favor the side with more molecules, because then it would increase the collisions, and there's more molecules to collide, so then it would increase the pressure again. But now they want to know the conditions necessary to maximize the yield. So we want to get as much methanol as we can. So we want to favor the forward reaction. So we know the forward reaction is exothermic. So exothermic reactions are favored if we cool the system, because exothermic releases heat, so it heats the system again. So we know then if we cool the system, it's going to favor the forward reaction to heat it up again. So it will be a low temperature. And then if we increase the pressure, it's going to favor the side with less molecules because we want to reduce the pressure. So if there's less molecules can collide and it will reduce the pressure. So the answer is C, low temperature and high pressure.